Okay, so we will start from the very basic definition of remote sensing of forestry. So actually, as we already explained that remote sensing is the acquisition of information about any area or any object on the surface of the earth without having any physical touch with that area, or without having any physical contact with that area. So the same definition goes with the remote sensing of forestry, that it's actually the process of gathering information about forest resources. So today our interest is a forest, without coming into physical touch with them in order to manage the forest, conserve the forest for human, wildlife, and environmental benefit on sustainable basis. If you go with the, for example, management of forest, you have to keep in mind three things. To manage the forest for a human, because forests give a lot of tangible and untangible benefit to humans, and also there are present wildlife in the forest, or biodiversity present in the forest. So we have to conserve also these for wildlife, as well as environmental benefits. So forests, you know, that have a lot of environmental benefit in the form of air and soil, water conservation, something like that. So remote sensing actually is the process, remote sensing of forestry is the process of gathering information about forest resources specifically without coming into physical touch with them. Yeah. So the same came, for example, we have spaceborne satellites images and airborne aircrafts or airborne drones. And also we have these TLS ground-borne technology. So these data are taken from the forest by using a different kind of sensor from space, air, and ground. And we put this data into the computer with the help of ground truthing, because we have to do also forest inventory by making a model between remote sensing as well as the ground. And finally, we have an information in the form of classified maps that I think you already know about it, because from the last 3 days we are discussing this. Yeah. Okay, so there are a variety of applications of remote sensing in the field of forest sciences. And I think currently we will get every information about forest. As from the last 2 decades, remote sensing has brought revolution in the forest mapping. And nowadays, almost in the developed countries, remote sensing, specifically the LiDAR technology, is using in operational forest management. So in applied research, they are continuously scanning their forest resources and they are getting different kind of information. We'll discuss this also today. So the very first definition of application of remote sensing, if you can see, deforestation. So as you know, that deforestation is actually the clearance or clear cutting, or is the removal of a forest or a stand of a tree from land that is then converted to non-forest uses. So it's totally a clearance or a clear cutting or removal of forest. So if you take the example of Pakistan, we have a large geographical forest area which are located on the border between Pakistan and Afghanistan. We have some very dense forests in Kashmir, also located on the border. And also our forest is really on a large geographical rugged mountain terrain. So if you go physically to that forest and try to estimate that how much area have been cut and where this area have been cut, it's very difficult. It's out of the reach of humans, I mean. And also we don't have any such resources to physically do ground inventory or something like that. But as you see, this is one of the sites which is located in Razmak Valley of Pakistan. Also, the line order situation was also not that much better there. But we use some satellites images, and we calculated some NDVI, like normalized difference vegetation indices, before and after, and then we make some differences before and after, and accordingly we estimated some difference that where, for example, this is one of the NDVI we calculated for 2015, and this is another NDVI for the same region in 2020, and this is actually the difference map, which clearly show the color is going to be black. So NDVI is something like when forest is low, the color will be low. When forest is high, it will be a little whiter. So we identified approximately some 10 sites where forests have been clear felled in the Razmak Valley of North Waziristan, Pakistan. And further, after automatic detection of the deforestation sites via indices differences, we visually identify further by using the high resolution satellites images like this. And you can clearly see that, for instance, here in 2015, the entire area was covered by forest, but even in 2020, so these areas have been clear felled. So now we have, for example, the data. So approximately some 125 hectare area have been clear felled from one test sites in Razmak Valley of North Waziristan. So that's one of the reasons that remote sensing help to estimate the rate of deforestation or the clear felling, which is totally clear felling of the forest. So we will give this data to the forest administration for rehabilitation, replanting, or something like that. Yeah. So similarly, we identify, I take one other example from the same sites in Razmak Valley. If you can have a look by using, for example, the deforestation NDVI before and then after, and then making difference between the two sites, we calculated that here the blackish color, for example, the blackish tone indicate that there is something happened in the forest area. So we identify automatically automatic detections, but after, for visual interpretation, we use some high resolution satellites images, and which we can clearly see that forest was present before in 2010, for example, here. And then if you can see the same area with the yellow color polygon, the forest area have been clear felled. So by this way, we will estimate the deforestation sites, or the sites which are totally clear fell by anthropogenic activities, can be detected with remote sensing without physically going to that sites. Like that. So deforestation or the rate of deforestation can very easily be monitored using remote sensing technology, or using a variety of, for example, remote sensing sensors. Yeah. The second is we go to the forest degradation. Forest deforestation is a little different, because forest deforestation is actually the clear felling of the forest and the clear felling of the cutting of the forest. That is actually forest deforestation. But forest degradation is the reduction of the capacity of forest to produce goods and services. Or in simple words, it's actually decrease its density. So if somebody is cutting, for example, single trees in the middle of a forest, so it will be a little difficult in the satellites images to detect these single trees. But although we are using a variety of remote sensing data sets to estimate the density of forest before and after, So for instance, if before the change that was in 2017 and that is in 2019, so the change is in negative. For example, if you calculate some differences of digital number or indices differences, if the change is in the negative direction, it means that here some reductions or some trees have been cut down. But if the change is in the positive direction, it means that here the growth of the trees have been happened or some trees have been planted. So forest degradation, it's a little difficult in the satellite images to estimate a single tree which is standing in a very dense forest environment. So for that, you can even use the drone technology where it is possible to detect even a single tree. We will discuss in later on about also drone technology. The third is, for example, as you know, afforestation or reforestation. So afforestation, as you know, that it is actually the establishment of a forest or stand of a tree in an area where there was no previous tree cover. Suppose, for example, we have some barren land in the southern Pakistan, where actually there are not that much forest. So if you can do, if you develop a forest in an area where there was a not present previous vegetation, so if you're doing plantation, that is actually afforestation. Reforestation is actually the natural or intentional restocking of existing forest and woodland that have been depleted usually through deforestation, clear cutting. For example, if you can see my first slides, if I give this data to forest department to do a replanting of that area which have been cut it down before, that will be a kind of reforestation. But if in that area there was not present previously vegetation, that will be afforestation. So afforestation sites can be very easily detected via remote sensing technology, via satellites data. For example, we have in Pakistan this billion trees afforestation projects going throughout the Pakistan, when government plan million or billion of Pakistani rupees to increase the forest cover in Pakistan. But one of the main problem and one of the main questions which every common man is asking, that okay, you have planted a lot of plantation, but actually what is the successful rate of this plantation? Because a layman also know that plantation is not a difficult task and it can be very easily done. But the plantation need continuous protection as well as conservation till a successful establishment of these plantations. So if you want to estimate the progress of plantation, or which is actually called afforestation or reforestation, that can easily be monitored via remote sensing satellites technology or with your airborne laser scanning. We'll discuss this later on, step by step. So afforestation and reforestation can also very easily be monitored using remote sensing technology. So if I summarize the remote sensing data, for example, we have airborne laser scanning data that is actually an aircraft which emits its own light to the ground, and then the light reflects back from the ground, and then we are getting a 3D information about anything on the surface of the earth, whether it's a tree or whether it's a human or whether it's an animal or whether it's stones or maybe canal, something like that. So I would rate airborne laser scanning that this is one of the most accurate options, and this technology is used in operational forest management in many northern country or Scandinavian country or maybe some other advanced countries. So they are continuously scanning their forest resources, and accordingly they are getting information about the forest cover, forest trees heights, and tree cutting, deforestation, or afforestation, or reforestation. So airborne laser scanning is one of the most accurate options, and I would like to rate this in number first. Second is actually the stereo aerial photogrammetry camera. That is also a kind of airborne aircraft. When it takes stereo aerial photograph. Like for example, one photograph have overlapping on another photograph. So this will be a kind of 60 by 30 sidewise overlapping and 30 by 30 endwise overlapping. Or sometimes we are increasing the size of the overlapping to get more accurate results. So we have nowadays the image matching algorithm which actually work on stereo aerial photograph. So this image matching algorithm actually using two stereo aerial photograph, and with the help of if you go back, that was a kind of stereoscopic pair which we usually see one object and two different image to know the depth of that object with the help of stereo machines. But now we have this image matching algorithm. This automatically generates 3D point cloud, and the data is just like, for example, airborne laser scanning. So with these 3D point clouds, we can also get the canopy or tree heights of a forest. And if you have a 3D points of a forest, 3D canopy height of the forest, then this 3D point can be used for a variety of applications, like for example, forest heights, single tree detection, canopy differences, or something like that. So in my case, the first is airborne laser scanning. The second is UAV drones, and also the UAV drones. What we are using, there can be also airborne laser scanning as well as this stereo aerial photogrammetry camera by using image matching algorithm to generate 3D point clouds, 3D image based point cloud for the forest surfaces. So these and the third is I would rate the, for example, this stereo aerial photogrammetry camera from the aircraft. But this airborne laser scanning of, or for example, this overlapping aerial camera from aircraft or beechcraft can be used for bigger area. But drones imagery can be used for a smaller area, but in a very intensive forest management that can be used. Apart from that, I would rate the spaceborne active sensor, for example, these satellites, spaceborne active satellites, which emits its own light to the ground, and then it go back. And then by applying some radar grametry techniques or interferometry techniques, we are getting the height of a forest or height of the elevation or something like that. So finally, I will rate this that spaceborne passive sensor, all the Earth observatory space satellites. This is also good, but we will get some. But from spaceborne satellites images, you have to keep in mind that we will get only 2D data, not 3D data. But nowadays, the stereo spaceborne satellites images are available, which we are applying this image matching algorithm, and from this image matching algorithm, we are also getting elevation of a forest for any area. I have a very interesting paper. Maybe I will share later on in the discussion. So the data sets which can be used, as I told you, for afforestation, reforestation, or deforestation, which call it ARD. This can be used airborne laser scanning, stereo aerial photogrammetric camera, UV drone, or spaceborne active sensor, as well as spaceborne passive sensor. These are some of the methods. For example, if you want to detect the, for example, visual digitization, you can detect the difference between the forest cover, and you can easily detect how much area can be deforested or afforested or reforestation. Post classification can also be one of the options. If you classify forest before and if you classify forest after, and then you just make a comparison between pre and post, you will also get some information about the rate of afforestation, deforestation. Image rationing is also one of the techniques that we are using by dividing one band on another, and then we are getting some information of change detection. We will just also use image difference is also, for example, when you subtract one band before and one band after, you will also get some difference. So the difference will be either increase in the forest cover or either decrease in the forest cover. Multi-date classification is also same as example of post classification. Change vector analysis, the pixel is expected to change in the spectral space, which is represented by a vector. Canopy height differences, for example, when you calculate the height of a forest before, and if you calculate the height of the forest after, and just if you make a difference, subtract one canopy height model before and one canopy height model after, you will clearly see that where the forests have been clear fell cut or the forests have been increased. For example, you will see the difference either in negative direction or in positive direction. So the difference in the negative direction will indicate that here trees have been cut it down or forests have been cut. Or if the direction is in positive direction, it means that here the trees have been planted or the tree growth have been increased. So this is even possible. And also indices difference is also one of the techniques that we can use for forest change detection. Like if you just calculate, for example, some indices like NDVI before and after, and you just subtract one from the other, you will get some difference of the forest cover that where forests have been cut or increased, something like that. So this is actually a little bit about that how to estimate afforestation, reforestation, or deforestation using remote sensing technology. The second, this is also one of my study that was taken in the forest of Deforestation. It's actually a kind of time series analysis of forest cover dynamics and its conversion to other land use land cover classes. So first, for example, this is based on spot satellites images. We took spot satellites images of 2004, and then we took these satellites images of 2007 and 2010 and 2013. So we calculate the forest cover in 2004. First, we classify that satellite seen in 2004, and then 2007, and then 2010, and then 2013. So here is the table which give you information about the forest land, rangeland, agriculture land, barren land, glacier in 2004 and 2007 and 2010 as well as 2013. And here is the last portion, which column, which is the difference of the area of forest as well as the rangeland or agricultural land between 2004 and 2013 in hectare as well as in percentage. So if you can do this kind of studies that is actually fall in the time series analysis of forest cover dynamics, you can easily do just by taking selecting satellites images at different temporal depths, and then classify the satellite image before and then after, and then just make a comparison of land use land cover that okay, before the forest was 36%, but in 2007 the forest was become 34, so it's a 2% decrease have been occurred in the forest. But this will give you only information about that forests have been increased or decreased. But for rehabilitation, for management, or for conservation purposes, you have to do a little more work, that whether the forests actually have been cut it down and to which class these forests have been converted. This was further done, we did further done this study, and we calculated, for example, this map shows along with the different color that, for example, for instance, this first color shows that these are the area where agricultural land have been converted to barren land. And how much this land have been converted, it is written here that, for example, agriculture land have been converted. So how much area in hectare as well as in percentage, and what is actually the exact location. For example, the remote sensing will give you information about the exact location where changes have been taken place from one land cover to another. So this is, you see, this is one of the map which clearly tell you that where exactly the change have been taken place. And beside this map, we have this detailed table, and this give you the statistic of their changes in hectare as well as in percentage where the changes have been taken place. So this paper is already published in the Journal of Mountain Sciences, and you can download if you want to study more about that how forest time series analysis of a forest cover and its conversion to other land cover changes can be done using remote sensing. Now we are coming to 3D mapping of a forest. So as I told you that the first was a kind of 2D mapping, like just was linked to the forest cover. So it normally fall in the area of 2D mapping. So now we are coming to the 3D mapping, which is actually called a three-dimensional structure of the forest canopy. So I have a very interesting paper that is published. You can have a look and you will see. So here in 3D mapping, the first information which come from that is actually forest height. And you can just imagine the forest area, the large geographical forest area across Pakistan and the mountain of Himalaya, Karakoram and Hindu Kush. If you take an instrument, if you go into the field and by measuring every tree in the field, height of every tree in the field, I think it is not possible. It will take a very large amount of time, but even in a simple word, it's not possible. But if you have remote sensing data, like here I use in this study, like comparing the potential of stereo aerial photograph, stereo very high resolution images, and tandem X for estimating forest heights. That's actually in the International Journal of Remote Sensing. So you can easily calculate the tree height of every tree height. And tree height is the parameter of a lot of importance, because if you have tree height, then you directly predict your DBH, diameter at breast height point of a tree. We have regression, because a tree height in DBH has almost 99 or 99% correlation with each other. So if tree height is increasing, the DBH is increasing. If tree height, so this has a direct relationship. So if you have tree height from remote sensing, you can predict your DBH. So if you have tree height as well as DBH, then you can calculate volume of a tree. If you calculate volume of a tree, you can predict biomass of a tree. If you have biomass, you have carbon stocks of a tree. So all the other parameters can be predicted by using different regression techniques, like single or multiple, something like that. So with the first parameter with 3D is like measuring forest height. It's usual traditional forest inventory techniques. It's laborious, it's time consuming, and it's excessively expensive for large forest area, where remote sensing single stand and large area can be covered cost efficiently. Although some small forest area and a plain area can be done even with an instrument, but if it's a rugged mountain terrain, like in Pakistan, we have this Himalaya and Karakoram as well as the Hindu Kush. You have to use the remote sensing to calculate the height of every tree. So that's possible with the remote sensing. Okay, so these are my two papers that was there for already published, but that was the study sites in Germany, not in Pakistan, but still, we are working also in Pakistan. The second important thing is the forest timber volume. So the forester know the importance of forest timber. This is actually the basic information where if you go to forest, if somebody tell you to manage the forest on timber-oriented basis. So timber-oriented forest management. It's an area where you have to cut the forest sustainably. You have to cut the forest, but at the meanwhile, you have to leave the forest in a condition same for the future generation. So, for example, we have a kind of rotation age for every tree. For example, in Pakistan, for instance, for chewed pine forest, we have 100-year age, for example. So if we have a forest, sometime we are dividing the forest into 100 equal parts based on the rotation age. So on every year, we are cutting, for example, one part, and a second year on second part, and third year, third part. Although in chewed pine forest in Pakistan, we are using like 1 to 25 year or 25 to 30 periodic blocks silviculture system. But if you are managing your forest based on the volume, so the first thing you have to know that how much volume is present in your forest, timber volume. So for instance, if your forest have 1,000 cubic feet, just an example, 1,000 cubic feet. And if the rotation age of that forest is 100, so you have to divide the 1,000 by 100. So it's mean that you have 10 cubic feet. So the forest management allow you only to cut 10 cubic feet wood from the forest annually. And that can be cut it from the old trees or decaying trees falls, and then come to the exploitable size something, and then come to the mature trees. But the primarily information we need for forest management or timber oriented forest management, we need to have information, a very accurate information about forest timber volume. What we are doing in Pakistan, we are taking sample plots. One sample plots, and then another sample plots, and then we are making a mean of all the sample plot, and then we extrapolate the mean on a large geographical forest area. But these sample plots is okay. So the first thing you have to cover the entire variation of the forest. That's you have to take that much sample plot that cover the entire variation. But in Pakistan, the forest cover. The forests are not even age. So the sample plot approach work very accurately in even age forest. But if you have an uneven age forest, if you have a lot of barren land inside of the forest, if you have a river floating inside of the forest, so and then you are using the sample field-based forest inventory techniques, and then calculating the means of that, and then extrapolating the results, I mean, that will be a little over exploitation of the forest resources. But if you make a model between remote sensing, trees height and volume, then this problem can be solved. So forest timber volume, which is actually an economic term, can easily be estimated by affordable mean, is one of the that's with remote sensing, and that's accurately information about forest timber volume by affordable mean. One of the primary objectives when designing forest inventory to forest management and operational forest management. So given the fact that in large forest area, it is not actually practically possible to measure all trees. And as I told you that the alternative approach can be a sample plots, but still the accuracy will be limited to sample plots only. So if you integrate field-based sample with remote sensing data sets, like make a model between them, that can be successfully used for generating a wall-to-wall mapping approach. What we are doing, that is actually in mapping of forest resources, we are actually applying two approaches. One is single trees, we'll discuss later on. And one is a wall-to-wall mapping approach. In wall-to-wall mapping approach, what we are doing, taking ground inventory sample plots, and then taking the remote sensing information and the exact location of the ground inventory sample plots. And between them, the remote sensing as an independent variable, the measure volume of the ground sample plot as an independent variable, and making a model between them. And then you can predict volume of the entire study area very easily. And you will generate a volume of any area. And you can easily extract the barren area, the water bodies and the glacier or some other building area with the remote sensing. That can be easily done. So forest timber volume can easily be assessed via remote sensing technology. And I have already published paper about forest timber volume. That is a kind of comparing airborne laser scanning and image-based point cloud by semi-global matching and enhanced automated extraction to estimate forest timber volume. That's in Forest Journal. If you can have a study in it, you will get much more idea about how forest timber volume can be estimated from remote sensing data. The second is, as you know, forest biomass. That's one of the important topics of forestry, because biomass is directly linked to the carbon stock. And you nowadays these carbon credits or carbon stock is one of the burning issue in the forest. Because if you just take the example of a tree, of a green tree, 25% of a tree is a kind of carbon in the forest, and 25% of a tree is another trace elements in the forest of the tree, and 50% of that tree is like, for example, water body. But if you become dry on the tree, then the water evaporated, and 50% of that tree become the carbon stock, and 50% of that tree is become the other trace element that is actually. So biomass of a tree referred to a weight or mass of a living plant tissue and generated. That can also be modeled from remote sensing technology. For example, if you have a tree height has directly linked. We have a lot of allometric equation for estimating biomass from a tree height. Even if we can calculate tree heights, and you can even predict dBH of the emitter press height of the tree, and you can even predict the biomass of a forest. If you have biomass of a forest, and it is clear that 50% of a biomass of a forest is a carbon, you can just divide the biomass on 2, you will get the carbon stocks of that. So carbon credits are the carbon sequestration potential of a forest can easily be assessed via remote sensing technology. But although if you are using airborne laser scanning, your result will be highly accurate. If you are using some airborne drone technology, your result will be much more accurate. But if you are using some space-borne sensor, so the result will be good, but not that much accurate as like high resolution, centimeter resolution data of drones are as well as airborne laser scanning technology. So remote sensing is also has a greater potential in assessment of the biomass, which is in turn, we call it carbon stock of any forest area across the region. And that can be needed in the future, because the underdeveloped country has a forest resources, and they don't have any industry. And the developed country has the forest, but they have a lot of industry. So these developed country will have to pay the underdeveloped country in the form of carbon credits. But for carbon credits, it's very important that first you will assess the carbon sequestration potential of the forest area of your region. If you don't have a data of your carbon sequestration potential of your forest, then it will be difficult to claim a carbon credit from the developed country or something like that. Yeah. Okay, so now we are coming to a very intensive forest management that is actually called a single tree detection. As I told you before, that we are using two kinds of techniques. One is area-based approach, which we call it wall-to-wall mapping. The second is single tree detection approach. We are detecting the height of every single tree. We are separating the crown of every single tree. So that's called detection of a single tree. So if you have height of every tree, and then you have the crown diameter of every tree, then you can separate it every tree. So if you have crown, if you have height, you can predict the DBH of every tree. You can predict the volume of every tree. You can predict the biomass of every tree. You can predict the carbon sequestration potential of every tree. Okay, so we actually individual tree detection approach, what we call it ITD. This actually involves separation of individual crowns, and the methods include for both 2D and 3D data, or what we call is a kind of watershed algorithm. So the algorithm start, if you have a canopy height model, first you have to have a canopy height model of the forest. These algorithms start from the top of the tree, and it's looking like a watershed. When it realized that there is no further increasing of the canopy, it make a polygon on every tree. Okay, and in the center, it detects height of every tree. So via this, we are calculating, we are detecting every tree with the crown as well as with the height of the forest. So as I told you, if you have this parameter, height of every tree, as well as the crown of every tree, for example, you can see, you can predict all the other essential parameter like volume of a tree, biomass of tree, carbon stock of a tree. And also, if you have a single tree, for example, I will show you today one of the case study that we conducted in Pakistan using drone technology. For example, if you have a canopy height model in 2010, if you can calculate a canopy height model of the same forest in 2020, if you just make a subtraction from one another, so the area where tree have been cut it down, that here the value will be in minus. But the area where tree have been planted down, here the values will be in positive direction. So even with the single tree detection, we can estimate now the rate of deforestation at a single tree level, which we call it actually forest degradation, which is actually the decreasing in the density of the forest. So by using a single tree detection approach, we can calculate every tree and its height, its volume, biomass, or other parameter in even the forest degradation, if there have been forest degraded, even the forest afforestation. What I'm recommended in Pakistan, for example, the forest department is spending huge money on the afforestation, and then they are going practically to the ground. What I'm suggesting to use a drone technology, just go to the field site and make a single flight of that area, and you will have all the information at a single tree level in a centimeter resolution of its height, its DBH, and you can easily tell to the public that here we did a plantation before there wasn't any plantation, but now we have this plantation at a single tree detection, because the afforestation potential in the mountain area, specifically if a tree is up to 1 or 2 meters, it's very difficult from satellite images, because the grosses of that area has a height of almost 1 to 2 meters. So in the plain area, it can be possible from satellite images, but in the mountain area, it will be a little problematic. What we are doing in Pakistan, we are using a high resolution satellite images, but still, I would say that in the mountain area, it will be problematic to assess the rate of afforestation or deforestation potential from even from a high resolution satellites satellites images. So this is can be also the single tree detection. This is also one of the study that we conducted in Pakistan. For example, I have a detailed case study for that we'll discuss later on. But you can see this is one of the DR plantations in the Single Valley of Pakistan. We fly a drone there, and accordingly we, for example, separated every tree, and we model every tree. So every tree have a height, And accordingly, we have, for example, single tree detection heights. But I have a case study. We will explain this in detail in later on in our case study. Yeah. Forest damages. This is one of the problem in the forest damages. For example, forest damages by disease and insect can easily be identified using the spectral information derived from the satellite images. Or disease tree can be separated via classification, image segmentation by using different non-parametric machine learning algorithms. For example, if you say some insect, when it attack on a forest, it using a specific host of a tree, so it follow a specific pattern in the forest. So if you detect this pattern, you can easily monitor, you can easily protect your forest resources from forest damages, which is actually caused by the insect or some other fungal diseases, or maybe some natural calamities. It's possible. So if you have a dry tree or detected tree, the spectral response will be totally different as compared to the healthy tree. So if you get the spectral information of, or maybe a disease tree, so you can easily classify that portion of a forest which have been diseased, which have been infected by a fungal or insect disease. And also, if you see these images, in my slides, the dry trees or the disease detected trees, here the spectral response is totally different as compared to the green tree. Because in disease tree, you know, when the chlorophyll contents become less, then automatically, because it is the chlorophyll which absorb the green color, or no, it is the chlorophyll which absorb the red color from the electromagnetic spectrum. So when the chlorophyll contents become less in the trees, it will automatically the absorption of the red color will be less, and the reflection of the red color will be high. As a result, you will see the trees with the yellowish. Okay, so I think we have to answer one question. Okay, number of trees per species can be counted. Yes, that's we have a case study. I will show you in my previous detail. No, with drone technology, as I told you, with the airborne laser scanning and also with the stereo aerial photogrammetry camera, we are counting every tree. And if you have every tree and along with the spectral information, you can easily classify the spectral information. You can use the spectral information for classification, and you can use the height, canopy height information for detecting single tree. This can be possible. This is possible, and we have this in Pakistan. Yeah, we have studied for that. Yeah, I will show you some. Okay, so okay. Okay, the second after that, you know, forest fire. This is one of the problem globally, but no, it's severe in Pakistan. If you visit, I mean, some month before, the Chalhoza forest in Balochistan was with the fire. I know we can see in the news that many fire incidents have taken place in the Hazara region, as well as in the Dir region, in the Swat region. This is one of the problem in Pakistan. As you know, that and also in the chur pine forest, this is very common. But wildfire is one of the prominent problem factor in most vegetation zone throughout the world, like forest and grassland. And wildfire present a challenge for ecosystem management because they have the potential to be once beneficial and harmful. Sometimes it's beneficial because it breaks the dormancy of the seed, but sometimes it's very much harmful because it burn everything, the microorganism present in the soil, even the birds and animal present in the forest. But despite the prominence of fire events, current estimate of the extent and impact of vegetation fire globally are still a challenge. So several 100 million hectares of forest and other vegetation types are estimated to burn annually throughout of the world, consuming several billion tons of dry matter and releasing emission compound that affect the composition and function of the global atmosphere in human heaven. If forest burning have taken place, all the carbon which is stored in the vegetation are released into the atmosphere. So when the carbon concentration is increasing in the atmosphere, the earth temperature will be increasing because this is the carbon dioxide which trap the back scattering of the electromagnetic radiation. As a result, we have a global warming problem. So these can be assessed in two ways. And that is, for example, early detection. Okay, for question, discriminate different tree species, FES, what kind of data, etc. Sen, Dr. Sadido Sen, you can use satellites data for tree species classification. I have one paper, you can use satellites. But for tree species classification, I would say hyperspectral satellites images. This is one of the most accurate options in satellites images, because hyperspectral satellites images has normally some 100 to 200 band, which can even differentiate a very common species, even pine, from one pine to another pine species. If you are using UAV drones, UAV drone can also be used. Because UV drone also have spectral information, but also from UV drone we are getting the height of every tree. So in satellites data, I would recommend hyperspectral satellite sensor can be the most accurate option. But we have a very good published paper from multispectral data, Sentinel data, Lancet satellite data. A lot of satellites data studies are available where you will easily discriminate different tree species from each other. Yeah, it's possible. If you just write on Google Scholar, you will find hundreds of papers. Hyperspectral satellite data will be the most accurate option among the spaceborne satellites sensor. Yeah, and from UV, if you acquire a UV sensor, a hyperspectral sensor, that will be much more better. UV hyperspectral, UV, because UV is actually a platform and you have to have a sensor with it. So the sensor, if you have a hyperspectral sensor, it will give you a very accurate result for different tree species classification. Yeah. Although the other multispectral data can be used, but hyperspectral data is much more better for tree species classification. Okay, so forest fire can be modeled. I mean, the area which are susceptible to fire, for example, in early detection, this can be modeled. This can be easily modeled. For example, if you have NDVI from optical data, land surface temperature from Lancet data, or maybe from our fuel moisture concept. Also, we have for this from remote sensing data, and you have ground data of some fire incidents. You can even model those areas which are highly susceptible to forest fire, and then you can do precautionary measure specifically in the higher temperature peak season. You can do precautionary measure. So this will be a kind of early detection pre-fire. You can even use a fuel moisture indices that can be vegetation and temperature indices, or water deficit indices with the temperature vegetation indices. And also we have some wetness indices, and that can easily be calculated from the different bands of the satellites images. And you can even detect some area which are highly susceptible, specifically in the temperature peak months, and you can even declare this area in the month of June or July, where temperature reaches peak season, specifically for forest. As far as the post-fire detection, it is very easy. For example, if there happen any fire incidents, there will be totally diminishing of the greenery of the vegetation. So if you have one satellite scene before the fire and one satellite image after the fire, you can do a classification of that. You can classify even the forest area via different classification algorithm, or you can use some vegetation difference indices, or you can do some other analysis post-fire detection. It's simply, for example, include mapping of burn area, or you can just, if it's clearly visible, the area which have been burned, you can make a polygon of that. So it's possible. Yeah. So remote sensing have really greater potential for the early detection as well as for the post-fire detection area across the globe, which is one of the burning issue in the globe because of the ever increasing temperature across the globe. Okay, forest types, we have very good study. This is also about forest types. If in Pakistan, if you can see if you start from Karachi, we have mangrove forest, and then up to around 100 feet, something like that. If you go a little up, which is to the southern part of Pakistan, up to 200 or 300 feet, we have tropical forest. In the desert, like we have tropical tan forest. If you go a little up in subtropical region, we have subtropical chewed pine, subtropical broadleaf forest, subtropical semi-evergreen or evergreen forest. And then if you go, if you come to the mountain of Pakistan, we have temperate forest. We have dry temperate forest and then moist temperate forest. And if you climb up to 11,000 feet or 12,000 feet, we have alpine pasture. I mean, subalpine and alpine pasture. So the forest types of Pakistan is totally classified on the basis of elevation. If you come, for example, 500 feet or 1,000 feet elevation, you will find different forest types. So it's mean that we have elevation-based forest types in Pakistan. The entire Pakistan is falling. If you go to the world climatic zone, it's in subtropical forest. But we have tropical forest, subtropical forest, temperate forest, and alpine forest. These we call it modified forest. And this is only because of the elevation, that we have all these elevation in Pakistan. So we have in Pakistan elevation-based forest. The second, we have temperature. If you go to the tropical forest, the temperature will be high. If you come to subtropical forest, temperature will be less. If you come to a temperate forest, the temperature will be much less. If you go to alpine pasture, the temperature will be very less. So we have also temperature-based forest. Okay, this is awesome. And we also have, for example, some other parameters, spectral response. Tropical forest will give you a different forest response, and subtropical different because of different vegetation. And as I told you, the different vegetation give you a different response. So for every forest, we have different temperature, we have different humidity, we have different land surface temperature, or we have different elevation. So if you use all these parameters as an explanatory variable, then you can easily model the forest types of Pakistan. You can model the entire forest types of Pakistan. So sometimes, you know, I face a problem in this study. That was my student who recently graduated from China. We face problem from differentiation of oak forest versus pine forest. Because it was very difficult to get the spectral information different between oak forest and pine forest. But oak forest was actually in Pakistan allocated up to 5,500 feet elevation. That was almost the peak. And from 5,500 above, the pine forest started. When we add the elevation information in the model, we were getting successful by differentiating between these two forests. But after it, we add the spectral information, the land surface temperature information, because the lower the elevation, the temperature will be high, the higher will be the elevation, temperature will be less. So that will increase much more our accuracy. What we face another problem, for example, we face the top of the houses. It's like thin. So the response of the top of the houses was same as we get response from the top of the mountain of the glacier. But when we add the information of the temperature, we were successful to differentiate between these two. So by applying different information like spectral information, elevation information, surface temperature, and some indices, you can even develop different indices. Like for example, for building, build-up indices, water indices, vegetation indices. So by putting all these indices in a single model and then predicting the forest type of Pakistan, we get very accurate result, and we have this paper. So forest type can very easily be modeled, very easily can be assessed, or very easily can be mapped from remote sensing data. This is also one of the potential applications of the remote sensing in forest type mapping. Yeah. This is our recently study, which was conducted by one of my PhD students who is working with me. This is one of the problem in Pakistan. What we are introducing species, like we introduce, for instance, eucalyptus. But we planted that eucalyptus. Okay, I think I have to shift the screen because the light. I have to change the screen. No, okay. So I think no, it's visible. Okay. So what is the problem actually in Pakistan, that when we are introducing one species from other country to Pakistan, to call it exotic species, we have two species. What is indigenous species, and the second is exotic species. Okay. So for introducing the exotic species to inside of Pakistan, we never did any suitability studies in Pakistan. But as you know that every tree species has its own parameter. So every tree species need, for example, a specific temperature, a specific soil type, a specific rainfall, a specific elevation, even a specific slope, etc. Okay, so I think I have to give one question. Okay, so okay, this is just a question. Hi. Okay, so if we can calculate all these parameters: temperature, rainfall, humidity, soil condition, the slope, elevation, etc., and we can easily predict or estimate the most suitable sites in Pakistan for that specific plantation. And we are going in this direction because one of the main reasons in Pakistan that we have some 70 to 80% area in Pakistan is arid and semi-arid area. And that's one of the reasons that we have a very low forest cover across the Pakistan. Only 10 to 15% we have some humid or semi-humid area in Pakistan where you can have these pine forest. But all the other area in the Punjab, as well as in the Sindh province, as well as in the Balochistan province, we have this arid and semi-arid area, and we have a large barren lands in this area. So we have to introduce some species, but before that we have to do some suitability study, and that we have to apply some criteria decision analysis. So if you have all these parameters and you can apply this decision criteria analysis. Let me see if my internet is working or not. So I'm visible. Okay. Okay. So this kind of study can also be done. For example, in this study, we apply multi-decision analysis criteria for the introduction of Jatropha species in Pakistan, and we map those areas which are highly suitable for the introduction of this species. And this Jatropha is a kind of energy crop which have a lot of environmental values, positive, a lot of medicinal value, and it can also be used as a as the demand of the timber or for fuel wood or something like that in the Pakistan. So this also we have a published paper in the Journal of Forest. You can have a look for much more detail. Okay. Okay, this is a problem in Pakistan also, because this monitoring of encroachment in forest area. So we have a lot of encroachment in forest area, and sometimes we don't have record of the forest area. So people are coming and they are making their home, they are converting the forest area from forest into agriculture, or they are making some building in it. But sometimes it's a forest area. So if you have a satellite images before and you can have a satellite images after, you can easily monitor the encroachment in the forest area. This kind of study can be detected via simple digitization, or maybe classification, or maybe the other advanced techniques in Pakistan, or as well as this encroachment is common across the globe. And you can apply remote sensing before and after for monitoring of the encroachment in the forest area. Forest biodiversity, as I told you, this is also one of the main concerns specifically for remote sensing. If you want to classify tree species as also one of the questions, discriminate between tree species for a large geographical area on the ground, it's humanly not possible. So we can classify even tree species, because every tree species have different response. And we can assess some species distribution, diversity composition, mapping of endangered species, species population, taxonomic coverages of tree species, habitats maps. We can do like this. Relations between spectral radiance value recorded from remote sensing and the species distribution pattern recorded from field observation can also be done from a remote sensing very easily. So this kind of parameter, like specifically in the area of forest biodiversity assessment, these the people are doing, the foresters are doing, and this is possible from remote sensing technology. This is also one of the questions, because wildlife detection and counting in the forest area, specifically, for example, poaching activities, the climate change, rapid habitat loss, and environmental degradation have led to massive population decline and even extension for many types of wild animals in recent decades. So the regular monitoring of wild animals is thus essential for estimating population changes, modeling the possible consequence of change. So what is the problem? For example, if there is no forest, if it's open forest, open barren land, if you have even a high resolution satellite images or aerial images, you can easily detect from multispectral data the number of animals, because we have, for example, template matching algorithm in the Python environment. If you just took a sample of an animal, and then you can train the software that, okay, this sample belongs to that animal, then this template matching algorithm automatically detect the specific type of animal, and it will make a polygon on the animal. And accordingly, you can even count and detect the number of animals in the forest. What the wildlife people are doing, because they are doing some inventory, and this is a little difficult because the animal are moving, they are going to one side, they are counting the animal with the sound, or maybe with the watching telescope. But it's a problem with the inventory, because the animal are actually moving not in one place. But with remote sensing in open forest canopy environment can easily be monitored via multispectral data. But yes, there is a problem specifically in a dense forest environment when the animal are present under the forest canopy. That's a problematic. But no, we have a thermal sensor, drones or thermal sensor, satellites images. If you have a thermal drone or thermal aerial thermal sensor in a drone or in aircraft or even from satellites, because these animal emit the radiation, the absorbed radiation in the form of thermal radiation. So you can easily even know possible to detect the wild animal, also the human, even the car movement of a car inside of the forest canopy by using the thermal remote sensing technology or thermal sensor. This is possible. Okay, so that was the end of actually the remote sensing, the potential of remote sensing in the field of forest sciences. Although there are a lot of other forest application, but you know, I think currently it's enough. So, for example, specifically in remote sensing, but to keep in mind that from the last few decades, remote sensing has brought revolution in the field of forestry. And to be honest, forest monitoring or forest monitoring is not possible physically on the ground. Specifically, the forest area is present on a large geographical forest area. And the most we are lucky because forest is actually growing on the top of the surface of the earth, which can easily be monitored from remote sensing. So remote sensing has a lot of future in the field of forestry. If one body think forest management or forest application without remote sensing, for me, it's not making sense, because without remote sensing, we can do nothing in the field of forestry. So this is the only possible solution that we use remote sensing for regular planning and monitoring of or valuable nature resources, that is actually the forest, for continuous planning and monitoring by using a variety of remote sensing data sets. So I think this is end for today. If you have any question, you can ask or you can write in the chat. We will have around, for example, it's now 1:11. We will have a 20 minutes break. After 1:30, we will start with some case studies. Today we don't have any practical, but we will. I will give you example of some of the case studies, maybe, and we'll discuss this afterward. And yeah, at the meanwhile, for example, if you can, if you have question or maybe some other thing, share your paper related to forest of Pakistan. Yes, Dr. Sadid. I think you can follow me on my ResearchGate. I have a lot of paper about Pakistan. Okay, I will share the links with you. Okay, all of my paper are uploaded on my ResearchGate on the Google Scholar. So and we are still working on Pakistan. So you will find all of my paper. Yeah, and I will share my email. You can just email also me. I will share the paper. Yeah. Okay, so Haris, are you there?
Yes, sir. So we're taking a break?
Yeah, we will take a break and we will come maybe after 20 minutes, okay? Right?
After 20 minutes. Okay. So
yeah.
The break, is it the hands-on or is it your second lecture?
No, it's a case study. It's a case study. So there is I think we don't have any hands-up training for today. Yeah. Okay. Okay, fine.
That's fine, sir. So let's say 20 minutes.
Yeah, let's say 20 minutes. Yeah. All right.
Okay, thank you.
Yeah, you're welcome. Okay.
Yes.
Okay, so I will give you example of few studies that we conducted recently in Pakistan. For instance, the studies, for example, UEV-based forest variable assessment using individual tree detection approach, comparison of small area broadleaf oak versus coniferous pine forest. So this is actually one of the study. Normally, if you go back, we have two kind of trees. One is pine and one is broadleaf. So we use this UEV drone. We fly the drone, and I think I will share you the video also here. You can just have a look, and then after that we will come to the presentation properly. Okay, So this is actually okay. Let me share this. Right. Okay, this I have to share, but this screen. So I think this screen is now visible. Huh? The video is visible, yes? Anand, can you see this? Okay. Okay, right. So let me start. This is actually one of the study that we fly our drone in one of the pine forest in Pakistan, and you can see this is actually a 3D model of the forest of one of the DR forest of Pakistan. It's not the original, but it's a model which was generated from the UAV drone technology. You can see we have almost every tree, and if we have this data, if data in 2015, and if we go back after in future in 2025, we go to the same site and we scan that with the UAV drone, we can easily detect that among this site, which tree have been disappeared or which tree have been detected. So you can generate this kind of 3D model of any forest across the globe by using the 3D, for example, UAV technology. Yeah. If we have, for instance, thermal sensor in this drone, then if there are present at least some wildlife even under the canopy of the forest, so these wildlife can also be detected from thermal sensor only. And nowadays it's available. I mean, you can buy only one platform of UV drone, and you buy 3 sensor, for example, multispectral sensor, thermal sensor, and even LiDAR sensor with it. Okay, so now that's actually one of the test sites of pine forest in Pakistan that we have generated the video of that. This is another test site, and I think this is it. Can you show me the? Oh, I started another video. Yes. Okay, yeah. So this is the same. We generated another 3D model for a broadleaf oak forest. And Okay, so yeah, I have to give some. Yes, Internet of Things for real-time monitoring. It's possible because these cameras etc. are directly linked nowadays with the real time by using different artificial intelligence. But actually, I'm not working on Internet of Things for real-time monitoring. Yeah, uh, my area is only using the remote sensing technology for forest monitoring. Yeah. But there are many people who are working on the Internet of Things for real-time monitoring. Yeah, yeah. Okay, so that was some of the. Let me show you one of the another centimeter resolution drone imagery of one of the forest nursery. Um, Forest nursery. In that is actually one of the forest nursery, and we scan with the drones, and that in forest nursery we have very small plants up to 1 year or 2 year. Yeah, up to 1 or 2 year hardly, but that can be very easily monitored from UAV drones, and you can see a small seedling of 1 to 2 meters are available, and you can visually see, and then you can visually classify from by using different some classification algorithm. So this is what I want to recommend in Pakistan to monitor the progress of plantation by using drones, small drones, because a small drone can uh, up to a small drone for 20 to 25 minute flight will cover a very bigger area. So this is I really want to recommend. Yeah, specifically for small area intensive monitoring. Yeah. Okay, so that was some of the videos that actually just for showing the potential of remote sensing, for example, for the potential of remote sensing, specifically the drone technology in the area of forestry application. That was actually my purpose, to that we can easily monitor up to detect or monitor every single tree in the forest, or we can even monitor a small seedling, as I show you one of the example of a nursery. Even for instance, we can monitor the broadleaf. I show you the example of broadleaf, a coniferous tree, and as well as one of the example of a nursery, forest nursery, where actually the trees are very small, up to 1 year or 2 year or 3 years. So if you utilize this technology, it will be much helpful in Pakistan. So this study we conducted, for example, in a UAV-based forest variable assessment using individual tree detection approach. We made a comparison between small area. Actually, it's a small area. We cover very small, and we selected oak forest. Oak is actually a broadleaf, and we selected pine coniferous forest here. So the motivation of that study behind was that, for instance, every year the government of Pakistan spend million on trees plantation, and people are not satisfied due to absence of a monitoring, evaluation, and reporting system. And also, it is a well-known fact that tree plantation is very easy, but it needs continuous protection from biotic and abiotic factor. So, and no, the question arises actually that what is the success rate of this plantation, and for this we need to do many field visits to physically verify the situation on the ground, which is very difficult due to limitation of resources and manpower, etc. So to overcome this problem, remote sensing play an important role in the planning and monitoring of the current status of plantation across Pakistan within limited period of time. Yeah, this. Also, as I told you, that was I give you example that among remote sensing, I told you that airborne laser scanning is one of the most accurate option for forest monitoring, forest plantation. This for small area forest monitoring due to repetitive fly expenses. But you know that airborne laser scanning is for example, one of the most expensive option also, because you have to fly your aircraft and then you have to scan the data. Although my next case study is about airborne laser scanning in Pakistan, we have this technology now. These airborne laser scanning with the Pakistan Army. So we are lucky enough that we have this technology in Pakistan, and the Pakistan Army are experts in flying that. And I'm also dealing the R&D section of that, and we are getting different information. Earth resource observatory satellites are already used for forestry plantation monitoring and across Pakistan. But as I told you, it cannot be successful in mountain plant monitoring such a small seedling. Spaceborne active sensor also has limitation, and monitoring of small plantation and seedling stage can be difficult. The only feasible data set is UAV drones, as I told you, which can be easily fly over small plantation sites having a centimeter resolution. So it has a centimeter resolution, and from which we generate digital surface model, DSM and DTM can also be generated. Okay, so the objective of that study was to estimate, to extract different meaningful forest structure parameter, like for example, the first was to count the number of trees, that how many number of trees are there. The second was to predict the diameter of the tree. The forester know diameter is actually the girth, diameter of the girth. which is actually the breast height point, and volume from a UEV canopy height model using individual tree detection approach. And we selected two sites. The first was the pine forest, that is actually the DR forest, and the second was oak forest that we selected in Pakistan. Materials, very simple, as I told you, that we fly our drones. For example, UAV drone that was inspired to UAV drone. And from that drone, we took the stereo aerial photograph with 80 by 60 overlapping, that we call it stereo aerial photograph. And this stereo aerial photograph were ported to an algorithm, image matching algorithm, and from which we generated, for example, 3D point clouds. So if you have stereo aerial photograph and you open this image matching algorithm, for example, there are a variety of software available for processing of the stereo data. For example, we use these Pix4D processing software for generating the 3D point clouds using the stereo aerial photograph taken from the drone. And from when you have 3D point clouds, you can easily calculate the digital surface model, which actually represent the top of the tree. And you can generate digital terrain model, which actually represent the bottom of the tree. So if you have digital surface model, which is actually this top of the tree, and you have digital terrain model, which actually represent the ground of the tree. If you subtract the digital terrain model, or you subtract digital terrain model from the digital surface model, then you will have a canopy height model, which only represent the forest canopy. Okay, so digital surface model, top of the tree, and digital terrain, the ground, and then if you subtract one from each other, you will have the canopy height model information, which actually represent the forest canopy. In this canopy height model, we further applied different algorithm, as I told you that we have, like for example, watershed algorithm and some other single tree detection algorithm. We actually apply this in our statistical software. As a result, we have that information. We have, for instance, two kinds of information. One was the top of the tree, and the second was the canopy. The canopy covered the crown of the tree. So top of the tree and the crown of the tree. So we have the height of that tree and as well as the width and length or the area of the crown of the tree. That was the result. The result, if you see, we have single tree height. That is actually, we have also direct height from remote sensing, but we also have some predicted height. Like for example, this RH stands for remote sensing height. And this is actually the function we get. We multiply with 0.49 plus 5.2. That's the function we developed from regression. And we got a coefficient of determination, actually 0.51. And we got 2.9 meter error with the tree. Like that was kind of 22% root mean square percent. Similarly, for tree DBH, which is actually in centimeter, we got this function. And we get this coefficient of determination, adjusted R square, root mean square, and 15% root mean square. And also finally, we have this tree volume for these mountain sites, and 14% for timber volume. We got a little higher. These are the final scatter plots of our results that we get from our analysis, and these are the final maps. For example, this detect that a single tree, so it generates points on every top of the tree, and after that, if we have height, we predicted the height of that, and after that we have the diameter, that is in centimeter for every tree. So this is the top heights. This is diameter, which we predicted using a regression. For every tree, and finally we have the volume of every tree, standing tree, and in that forest. So we can easily even calculate its age, because the more the height is, the more age will be, and this can also be regressed, or this can also be predicted by using the remote sensing. Yeah, this is also possible. Okay. So this is the another site that we did for the broadleaf forest. Actually, for broadleaf forest, we got the single tree height, that is in meter, and single tree dBH, and single tree volume, that is for oak forest in Pakistan. And you know, this we got for height, we have 0.68 coefficient of determination. For tree dBH in centimeter, we have 0.40. And for volume, we have 0.42. And accordingly, we got the adjusted R square, root mean square, and this. And these are the scatter plots of the results for the single tree observed versus the predicted. And we have this, for example, map finally. For example, every tree top was detected with a point. And accordingly, we have height of every tree. So the first was counting. We count every tree, that how many number of trees are there, and we calculate height of every tree from that. And accordingly, we have centimeter dBH of centimeter of the broadleaf, and we have finally the volume of every tree of a forest. So we successfully demonstrated the potential of a UAV drone for a single tree detection parameter, single tree detection parameter in both broadleaf forest as well as in the coniferous forest. So because normally forest can be pine forest, which we call it coniferous forest, or forest can be broadleaves, which we call it broadleaf forest. So up to single tree level, which we call it intensive forest management, we can detect from remote sensing. So that's I think our evolution. I mean, we can model every tree and its a parameter. Okay, Wakar. Okay, you can ask Wakar a question. Horace, if you can allow Wakar. Ahmed, if you want to ask a question. Wakar, you can write in the chat box your question, okay? Because I think Horace is maybe busy. You can write in the chat box. We will discuss this later on. Yeah.
Are you getting me, sir?
Yes, Wakar. Okay, please.
Which software package we have used for this workflow?
Actually, for first, for when you get the stereo aerial photograph, okay, we use Pix4D capture. We use for then, and also Pix4D for the generation of 3D point cloud. So after that, we use the ArcMap for the generation of canopy height model. Like there is an option in ArcMap of importing glass data into ArcMap. So in ArcMap, you have the option to generate digital surface model as well as digital terrain model, and you can use the raster calculator. After calculating the canopy height model, we use the R statistical software by separating every single tree. Yeah, every single tree. And in the same R statistical software, we use the modeling like regression modeling also in statistical software. So in this study, we use some tree software, Pix4D, ArcMap, as well as and the R statistical software. Yeah, so you have to use a variety of software to get meaningful information. So this clear, Bakar?
Yes, sir. And
yeah.
sir, you have used aerial photographs.
Yeah,
I think.
yeah.
Can we use satellite data for this workflow?
Yes. It's possible because now we have stereo and trio pairs satellites data, okay, even. But you know, the result will not be that much good as we have from the aerial photography drone data. In aerial photography, we have a lot of the point clouds, maybe some very dense point clouds per meter square. But with satellite data, you can even generate the 3D point cloud. But this satellite data can be stereo pair. If it's not stereo pair, you cannot generate a 3D model from it. But if it's stereo pair, then it is possible to generate, but still the accuracy will be very, very lower as compared to the aerial photograph or drone data. Yeah. Is clear? Okay. So the conclusion is that we successfully extracted different meaningful forest structure parameter at a single tree level, like tree counting, its height, diameter, and volume from UV canopy height model using individual tree detection approach. And you can even the other parameter like tree age, biomass, carbon stock can also be predicted via regression between individual tree remote sensing information and ground measured volume. So the finding of the proposed project will be used for continuous planning and monitoring of the progress of plantation across Pakistan. So actually the function, the purpose of my presentation, I put two studies, case studies for all of you. One is based on individual tree detection approach, and the second is on that. Now I'm going to tell you it's about a sample plot approach. We call it area-based approach, or we call it wall-to-wall mapping approach. So in remote sensing, specifically in the area of forestry, we have two approaches. One is individual tree detection approach, where you have to detect every tree. But this individual tree detection approach is much more successful in a high resolution data, specifically the aerial photograph, or maybe LiDAR, or maybe drones or something like that. But the other study which I'm going to tell you after that is about airborne laser scanning, actually airborne laser scanning, which we call it LiDAR, but that can be used for satellites data or something like spaceborne satellite, passive sensor, or spaceborne active sensor, specifically for coarse resolution satellites data, yeah, that we are using. So normally we have two approaches. One is area-based, and the second is the individual tree detection approach. So now we are done with the individual tree detection approach. The second, after that, we are going with the area-based approach by using another kind of data set. Yeah. So at the meanwhile, yeah, you can write her. So we are going to our next study. Okay. So that is actually not, I'm sharing the screen. Okay. Screen. Okay, this is actually this one. Okay, so I guess the screen is visible. Adnan is visible?
Yes, sir.
Okay, okay. So the next study, which I'm interested to discuss with you, that we conducted recently in Pakistan, that is about comparison of airborne laser scanning versus Sentinel-2 data. Sentinel-2 data is a kind of 2D data which are freely available. I put this for you just because if you don't have an option of airborne laser scanning, because it's one of the most expensive option even for developed countries, and for underdeveloped country or developing country like Pakistan, it's really expensive. But I work on airborne laser scanning during my stay in Germany. But when I come here, luckily I was lucky that we have these data sets. We have this sensor in Pakistan with the 477 Pakistan Army Survey Group, and I'm also working with them in the kind of collaboration. So I just show you that how it's working. It's actually comparison of airborne laser scanning versus internal. Airborne laser scanning is actually an active sensor which can be fixed on a beechcraft, okay? And if you are flying this beechcraft on any area, it emits its own light, okay? And these lights coming to the ground, and then this light reflects back to the sensor. What the sensor do, the sensor actually calculates the time difference. Okay, the echoes are the radiation which reflected from the top of the tree that will take a little small time as compared to the lights which come from the ground of the forest. The light come from the ground, it will comparatively take a little more time. So if you have time, if the light is moving with the known velocity of light, you can easily calculate distance from the aeroplane as well as to the ground. So it's working in this direction. So it's an active sensor which emits its own light for illumination of the ground. And as a result, we are getting everything. We will build everything. If it's a forest, it's a buildings, or if a car, if a human, or whatever, we get a three-dimensional shape of the earth surfaces, of any object on the surface of the earth surfaces. And that's a kind of 3D point clouds data in a loss format. We call it loss format. The second, with Sentinel-2, it's, you know, that it's the Earth Observatory satellites that was launched in 2015 by the European Space Agency. And these data are freely available across the globe. So if you don't have any option of airborne laser scanning data, you can even use the Sentinel-2 data for estimating above ground biomass, carbon stock in a subtropical chewed pine forest of. So that was one of the study. Okay. So the motivation behind that study was that forest ecosystem serve as a sink for atmospheric carbon dioxide in the form of biomass, and they play an important role in carbon sequestration and carbon cycle regulation. So, you know, the environmentalists also know the tree is actually one of the natural sink which took the carbon dioxide from the atmosphere, and it can store, and it, for the performance of photosynthesis, it absorb or it take carbon dioxide from the atmosphere. But when the tree burn or tree can be cut, these carbon dioxide even released to the atmosphere. As a result of, as you know, that as the carbon dioxide concentration increases in the atmosphere, we will be facing much more severe global warming, a kind of problem in the future. So as I told you that among remote sensing data set, airborne laser scanning is generally known as the most accurate remote sensing data for estimating forest biomass quantity. And as it has the capability to scan the entire forest canopy. What we are facing in forest environment, specifically while using stereo satellite data, for example, we just discussed that you can use satellite data for digital surface model. So in forest environment, you can build the top of the forest trees, but you cannot see the ground of the forest floor. This is impossible. I have a study, I have a published result on that. So the ground is in a dense forest environment, you cannot see the ground. Okay, so that's, if you cannot see the ground, you cannot generate digital terrain model. You need a digital terrain model, the ground, and digital surface model, which actually represent the top of the tree. If you don't have digital terrain model, if you have only digital surface model, it will not work for you. What I did in my study, I used digital terrain model from LiDAR and digital surface model from satellites, and I subtracted, so I got some of the results. So you need, so airborne laser scanning is an independent data set. This has the capability even to penetrate in the forest canopy. So it has the power to penetrate. So it gives the entire information of the forest canopy, from the floor, from the middle of the forest canopy, as well as from the top of the forest canopy. So this is one of the most independent remote sensing data sets which can be used for a variety of applications in the field of forest sciences. And that's only the reason this technological advanced country, as I told you, that are using LiDAR technology in the Scandinavian country. They are using LiDAR technology for operational forest management. They are continuously After every 4 or 5 years, they're scanning their forest resources with airborne laser scanning, and they are getting their information. Accordingly, they are getting a variety of information on the forest resources for planning, monitoring, and conservation resources on sustainable basis. So that was a little bit about LiDAR, but apart from 3D technology, such as ALS for study and assessment of, in Pakistan, we have this data, but that can be available for a smaller forest community in Pakistan, or maybe we'll have for a larger area. This is possible, but it will be highly expensive. So we have to pay a very handsome amount to Pakistan Army to acquire this data, because the aircraft can be flown up to at 3,000 meters, and it needs a lot of power to scan and something like that. So it's expensive data set. So apart from 3D data set, in this study, I tested this open source 2D space-bound sentinel data, which has also greater potential in Pakistan, even across the globe, for regular planning and monitoring of the natural resources. That was a little motivation. So if you take example of Pakistan, across Pakistan, few studies based on ground sample plots have been conducted, few studies. And that's actually only related to sample plots. They took sample plot in the forest, and according to sample plot, they used some allometric equation, and accordingly they calculated the biomass or carbon stock of that forest area. That's studies are available. But in Pakistan, to our knowledge, this study compared for the first time the ability of 3-dimensional airborne laser scanning with 2-dimensional Sentinel-2 data for the first time in Pakistan to estimate above ground biomass carbon stock in a subtropical pine forest of Pakistan. Although there are a lot of studies have been taken place in the developed countries, but in Pakistan, this we are doing in the first Pakistan. As I told you, if you can see this, this is a kind of beechcraft, and it's produced its own light, and the light falling to the ground, light coming to the canopy of the forest. So some of the light reflected from the top of the tree, some are reflected from the middle layer of the tree, and some are from the ground of the tree. So as a result, we are getting these kind of 3D point clouds data. We are getting 3D point clouds data. And the second, this is the Sentinel sensor, and this is working on the presence of sunlight. It's a passive sensor. The sunlight coming to the surface of the earth, and it passes from the atmosphere, reaches to the ground, and then it reflects back. And again has interaction in the atmosphere, and finally it switches to the sensor, which is present in the satellite. We get the 2D multispectral data. Okay, the study site was in Mansehra district of Khyber Pakhtunkhwa province, and which was just located on the river of Kunhar. So the elevation of that area was a little mountain, but still not that much. It was 1,031 and 1,400 meters above sea level. So the main species was Pinus ragbardii, that we call it chirp pine, but there was some associated species with Pinus populus nigra, Alanthus altisimia, Salix tetrasperma, and Ficus some broadleaf species, was there, So in these sites, we took some sample plots. You can see ground sample plots. We did ground inventory, and that was a kind of a systematic ground inventory we did. Like one sample plot was located around 250 meters from other sample plots. And inside of the sample plot, we measure the height of the tree and DBH of the tree, and accordingly we calculate the biomass and carbon stock of the trees, but at sample plots location. Okay, the biomass of a sample plot per hectare. So that was actually the flow chart of the research methodology. We have these LiDAR sensors. Okay, this emits its own light. We did this flight. And we scan that sites with the beechcraft, And from that 3D point clouds, we generated the digital surface model, as I told you, which represent the top of the tree. We generated digital terrain model, which actually represent the ground of the tree. And by subtracting the digital terrain model from the digital surface model, we got the canopy height model. And after that, we extracted some explanatory variable from that canopy height model. Like we calculate maximum height, mean height, standard deviation, coefficient of variation, and height percentile, and some density matrices at a sample plots location corresponding to the sample plot location. So these explanatory variable were regressed with the ground measured biomass as well as the carbon stock by using a stepwise regression model, and finally we got the root mean square or root mean square percent using bootstrapping techniques, which we applied layout one cross validation, where each observation can be removed as a testing, and the rest will be used as a training. So we split the data automatically by using this software or statistical software. So this algorithm automatically remove every observation, and the rest is used as a training. And the second time, the second use is dig it out, and the rest was used as a training, and the one is in the testing. And finally, by averaging the root mean square value of all, and then we got the results with field measure sample plots. As far as the Sentinel data, because that is actually a 2D data, we use that Sentinel 2 data, and that was what we derived from settled Sentinel 2 data. We derived spectral band because these 4 bands were already present in the satellite data, like the blue, red, blue, green, red, and infrared. And also we extracted some 15 to 16 vegetation indices from it. In these vegetation indices were regressed with the field measure, sample plots, biomass, as well as carbon stock, by using a stepwise regression model with the help of layout one cross validation. We got the result, and we apply, for example, a KQ information criteria. But I miss one thing in the methodology. Sometimes you have spectral band, you have vegetation matrices, you have to solve the problem of multicollinearity, because if there is a higher correlation between the bands or between the indices, you have to remove some of the bands. And we did this by using the various inflation factor, and the bands which were finally we got, that were used for the final modeling. So that was the methodology. So that was the result. You see, for ALS data, that we call it above ground biomass or above ground carbon stock, ALS data show 0.83 adjusted R square and also coefficient of R square. And this was the intercept and canopy density 1, height maximum. It's a little tricky, so you need to know much more about that. So we got a very accurate result as compared to the Sentinel-2 data. But for Sentinel-2 data, we still have a higher correlation, and this result can also be acceptable if you don't have an option of, for instance, if you don't have an option of airborne laser scanning. Yeah. So that's actually comparison of root mean square or root mean square percent. For ALS data, we got like 27.6%. The same for carbon stock, but for Sentinel-2 data, we got some 44.33 or 44.33% data. And the same with MAI and bias percent we got for that. So this is actually the scatter plots, which we use as a statistic between the observed and predicted, just for showing in a comparison. And these are the final maps that we get. For example, if you see here, the first map depicts the biomass per ton per hectare. So we got, like, for example, from minus 3.8, which was a little underestimation, specifically in an area where there was no forest, the model up to 26 ton per hectare. We got the biomass, and we got, for example, if you this is for airborne leather scanning. If you take 13, it is almost half of that 13.12 carbon stock per ton per hectare for the same site. And this is also the map of the actually from Sentinel. From Sentinel, we get up to 22 tons per hectare biomass, and also carbon stock 11.085 carbon stock per ton per hectare we got for Sentinel 2. So the conclusion is that despite the fact that LS technology has been established and tested in developed countries, Pakistan forest community is unaware of its potential application in the field of forest sciences. Not only Pakistan, but I would say the underdeveloped country, because I'm studying some literature. So from the underdeveloped or developing country, I hardly find any study that they are using the airborne laser scanning. So it offers a great potential in the field of forest sciences, and specifically the forest community across Pakistan will have to think about its potential application in the field of forest sciences. The goal of this study was to assess forest community in Pakistan with the perspective use and implementing of remote sensing technologies such as 3D LF data for various applications in the field of forest sciences. And that's also, I recommend, same for the rest of Islamic world, that they also have to think about the potential application of remote sensing technology, specifically the 3D LF data, because this has not only application in the field of forest sciences, it has a lot of application for delineation of watershed, for agriculture, for geology, or for other parameters, etc. So we successfully showed the possible use of 3D sensor for estimating forest biomass in subtropical chill point for the first time. However, it will need to be evaluated in future for Pakistan to other forest type as well. So we also examine, if you don't have the option of airborne laser scanning in Pakistan, okay, the other option is available with us, and that is actually, about the Sentinel-2 data, which are freely available up to 10-meter resolution. So that can also be used as an alternative for frequent reporting and monitoring of forest resources. So for instance, if you don't have ALS, so at least we can use the Sentinel-2 data, which are freely available and which is also a viable option, at least to monitor our forest resources, or just to think that we don't have satellites or remote sensing technology. At least we have the Sentinel-2 data up to 10 meter, or we have Landsat satellites up to 30 meter. In Pakistan, we have no Pakistan remote sensing satellites up to 2 meter resolution. This data can also be used for forestry application in Pakistan as well as in other countries. So regarding the application of 3D LS technology in 2D multi-experience and in combination with field data. So what we applied, we use a combination of field data, which we always applying at the ground truthing, defining you important information methods for provincial, national forest department, environmentalist, climatologists, and RED plus policy makers in Pakistan. So that was the end of my second case study that I was interested. So I think this is the end from my side today. So if you have any question, you can ask me, or you can just write in the text. So I will be here. I will be happy to answer you. Yeah. Any question regarding forest or something like that? Yeah.
Dear participants, if you have any questions, just raise your hand and I'll unmute you. Or if you want to leave a question in the chat for Dr. Sami to answer.
Okay, so we have some question. Thank you, sir. Okay. Ibrar Hossain, welcome. Yeah, Ibrar. Okay, could you please send me the today's slides and those of previous classes? My email address is Adam Bola. Haris, I think I will share all of the slides and you can note it down, this email with you.
Share
And
them all with me, all the relevant material that you want to share. Just share it with me.
Yeah. And you can share
Friday,
with
share it
them.
with all of them.
Yeah, you can share with them. Okay.
Okay.
Yeah.
So I think there are no questions.
Yes,
If
Haris.
anyone has any questions later on, you can email it to me and I will forward them to Dr. Sam.
Right. I'm agree. Okay,
one
Adam Bala have one. Okay, if you give an option to Adam Bala, Haris.
Go ahead.
Hello, good evening, sir, and thank you for the lectures.
Yeah, you are welcome. You're welcome.
Please, how can I be able to differentiate different classes? We know that like if you are carrying out a classification in forested area, there may be spectral signature mixed up in such a way that the shrubs and maybe larger trees may appear to have certain classes. So how can one be able to differentiate such? If you are trying to differentiate the grasses from the shrubs, from the trees, if you are carrying out long cover classes. Thank you.
Okay, Adam, if you are using LiDAR technology, it's very easy, okay? Because from LiDAR technology, you are getting height of the tree. You know, the grasses have almost up to 1 meter height. The herb almost have up to 3 to 4 meter height. And the tree, you know, have a height up to 20 or 25 meter. With LiDAR technology, it is very easily possible. It's not a problem. You can just go with the raster calculator and you can just classify your canopy height model into different layers, like up to 1 height. From 0 to 1 height is grasses. From 0 to 3 meter, it's from 1 to 3 meter is a herb or shrub, or from 3 to 25 meter or 30 meter or above, it is tree. So from 3D technology, it's very easy. As far as with the multispectral data, it's a problem. But still, you have to take homogeneous signature, okay? A very homogeneous signature. For example, you have to take a signature in the grasses, as well as you have to take a signature in the forest. I hope you will find a slight difference between the classes, because if they are not 100% the same. Grasses and shrub has a small difference. The other thing you have to think how to more detail. Specifically in the winter season, you know, there is no grass cover in the forest floor. So if you classify your forest in the winter, you will have only trees and the ground is without grass, or sometimes it's in snow in the winter. So you have to use a different combination of time. This is also possible. Specifically, agriculture crop, differentiation between agriculture crop as well as with the herb or shrub. You know, agriculture crop is not always present around the year. When there is no agriculture crop, you can take one satellite image from that time and you can subtract that season or that area, and that can also be things. But still, if you are using hyperspectral satellite images, as I told you, for tree species mapping, even we were successful with the classification of pine trees, which has almost 70 to 80% similarity in the spectral response. So hyperspectral satellite images have 100 to 200 bands, and they can really differentiate a very small difference even. So there are a variety of solutions you have to think. For grasses, herbs, shrubs, from LiDAR or 3D technology, UV drone, if you have height model, very easily possible. From multispectral data, it's possible, but it's a little different. But still, I'm sure if you train your classification algorithm, I'm sure it will classify your classes up to certain limits. But finally, when we have no solution, then we go with the manual digitization even to classify some area which is extremely difficult to differentiate between the spectral response. We go with the manual digitization even. But also, I would like to say that you can apply the object-based classification algorithm. Object-based classification actually make a polygon on a very small level. It will make a polygon on a grass, it will make a separate polygon on a tree, and it will make a separate polygon on an agriculture crop. So with object-based classification, I'm sure that your problem will be solved, okay? So you apply an acquisition software and using satellites imaging and the object-based classification. And after, when you have a polygon of every different object, you can just label it. So I'm sure your problem will be solved, yeah.
Okay, thank you so much.
Yeah, you're welcome. Welcome. I want to ask about the identification of landslide. Yeah, that's Dr. Shafiq is expert, and he's expert of natural hazards, and he have the lecture tomorrow specifically for landslide. So I'm sure he will give you a very detailed answer about that. Okay. How can we know the exact location of event happen in the forest if the landslide or event data is not available? Exactly, if the landslide data is not available, you have the temporal satellite data from 1990. Yeah, it's possible. Okay, so you can just use if the landslide happened in 1970. If you don't have satellite data, it's a little difficult. But we have at least Landsat satellites images from 1975 onward or 1980 onward for the entire globe. So these are available. Yeah. Yeah. Any other question if somebody wants to ask? Okay, Aris. So I think there are not more questions. We will end today with this.
So tomorrow is Dr. Shafiq from now.
Is there any exercise given so far? So I really request to at least generate a land use land cover map, because that was a kind of beginner course. Maybe later on through comstech, we come there physically for a more brainstorming remote sensing exercise. So at least that you guys get some idea to downloading of land satellites images and then the processing steps and the classification, etc. So at least I would expect that all of you who are present here generate a land cover map of your study area. At least that will be a good exercise for a beginner. Yeah. You're welcome. Yeah. Yes, exactly. Exactly. That's what I want. Yeah.
So hopefully everybody has copied the task. I don't think we have any more questions.
Yes,
So,
yes, yes. I think, yeah.
Yeah.
Yeah. Okay, Haris, huh?
Once again,
Yeah, you're most
your
welcome.
lectures.
Most welcome. Yeah. Thank you. Yeah, yeah.
Thank you.
See you then. Yeah, yeah. Take care.